All right, next time up we have Ian Ross to compare and contrast doing training of learning models in two very different environments.
All right. Thank you, TJ. So quick introduction. My name is Ian Ross. I've been with CHTC for 12-ish years. I've had a lot of different hats that I've worn over the years. Today I'm wearing the AI guy hat and the classical scientist hat. So we're going to apply the scientific method a little bit. We're going to start with an observation. I think Ava made this observation yesterday. AI is here, and it's changing the way that people are doing science. I'm not going to talk too much about exactly what those changes look like, what those modalities of AI-driven science really mean. I'm not going to talk about hype versus reality, other than pointing out that the AI-generated image that I always put in my talks about AI got about 3 panels into the 4-panel comic before it fell apart completely. That seems like a success rate I see pretty often with these things. I'm not going to talk today about kind of AI-driven software development. I think Nick had some really good open questions. I'll talk a little bit about it, like I said earlier on Friday. But what I am going to talk about today is an experiment to show that all of our favorite high-throughput computing principles, distributed high-throughput computing as a discipline, is applicable and powerful in AI-driven science. So, hypothesis. There is a huge amount of value and power in applying these principles to machine learning tasks, some machine learning tasks. It's not really going to be applicable in the giant foundation model type trainings, but there is a huge collection of tasks where it can be really, really impactful. So training ensembles of models, kind of small to medium size for some definition of small and medium, doing ablation studies of those models, basically anything that can boil down to give me a GPU for some amount of time and I will happily use it. And this might be GPU-based simulations or inferences. And then, of course, Condor has a lot of support for automation, and the facilitation team does an awesome job of teaching. And all these things are applicable in the realm of AI and machine learning. Today, I'm going to talk specifically about training. One of my kind of theories here is that training is kind of the hardest one. If we can prove HTC works for training by proof of induction, it should work for everything else. So, what are the objectives of the experiment that we're going to run? We're going to run a suite of training tasks, and we're going to characterize them. We're going to look at how distributed training across heterogeneous resources actually changes the impact or the prediction power of those models. And on the side, as we go, we're going to do some translational computer science. We're going to test our capabilities. We're going to advance how our access point works in kind of this new setting. We're going to try to reduce the barrier of entry for supporting machine learning workloads. If you were here last year, this diagram probably looks very familiar. So what is the actual methodology that we're going to do here? So we work with Tony Gitter's group. He was here yesterday. I don't think he's here this afternoon. But they do protein language model training. So they do training. They know these protein language models really well. We're going to take their training processes and we're going to kind of break them apart and do interesting things with them. So the way the training works, think of training as a long chain. Each link in the chain is forged by doing kind of a pass through your training data. You make some predictions. You look around, you say, oh, if I move in that direction, my predictions will get better. You take a step in that direction, and then you forge a new chain. And so the training process, every link in the chain is called an epoch. That's one pass through the training data. And what we're going to do is we're going to forge links in that chain at different sites as we go. So we're going to forge a link on one site. We'll take the checkpoint, take the weights, move it to a different site, resume the training, and just kind of see how it goes as we move around and around and around. At the same time, we're going to do some baseline training in CHTC, sticking to either a single host or a single GPU type for a validation set. Then once we have a bunch of different variants to compare, we're going to use a validation data set, and we'll look at the training behavior. Are these models converging similarly? And we're going to look at the science side of things. Are these models making predictions that are comparable? The model that we're training has a pretty good requirement in terms of the memory on the GPUs themselves. It requires about 60 gigabytes. the OSPool contributions, they certainly exist. We did a lot of our computing in the OSPool. But we know we've had users come to us and say that they need even more than this. So we also wanted to make sure that as we're going, we are kind of paving the way to make sure that users are able to get to more resources beyond the OSPool capabilities. So this is where NAIRR comes in. This is the National AI Research Resource. It is a NSF initiative that connects researchers to GPUs. You can get allocations at sites, you can move your work there and get the GPUs that you need. And so as part of this project, we got allocations at 5 different NAIRR sites: Anvil, AWS, Bridges, Delta, and Expanse. And we're going to mix those with the OSPool as we forge the links in our training chain. And we're going to use the NAIRR resources by using the HD counter annex. We're going to move all our data with the OSDF. And we're going to do everything as if it's local to a single AP. So a table of kind of grand totals here. To date, we've done almost 1,300 epochs of training, about 20,000 GPU hours. We've moved 43 terabytes of data. Every job is around 20 gigabytes, and it adds up quite a bit over time. We've run on 9 different GPU types. And then if you include the different OSPool sites that we've used, we've gone to 13 different sites across the country. And give you a sense of where things actually got done. Pie charts of where the epochs were finished and how much time we spent total computing at each one. You can see that, I think it's about 2/3 of the computing was done in the OSPool. About a quarter of that, we actually went out to the OSPool and came back to CHTC. Duke contributed some H200s for a couple months that, oh boy, we love to see those. But we also got good chunks from all the NAIRR sites as well. Anvil is the exception on this chart because this is just one model variant. Anvil, we spent our allocation on the previous variant. Okay, so now I'm going to spend a little bit of time about our observations and our analysis. So like I said, we forged links and some chains. Then we're going to take a look at each link and compare it across the different model variants that we trained. So we're looking at epoch 1. We're going to compare all the different models that we built, just the first epoch. And we'll look at the second epoch. And we'll do just kind of what are the mean and the variance of the predictions made by the epochs at that stage, right? So the red lines, it's pretty hard to see here because they overlap almost entirely, but the red is the CHTC baseline and the blue is the distributed heterogeneously trained ones. And this is a Pearson total score. It's essentially how well did the neural network model correlate with the baseline kind of true simulation values. You might spot at the very, very end, kind of at the end of our model, a little bit of difference between the blue and red curves, but that's more apparent in the test loss curve. And so this is pretty interesting. Again, the blue is the heterogeneously trained model. It's the one that went out to the OSPool. It's the one we're moving around all the time. The test loss actually dipped lower, but with much, much higher variance than the baseline models. So what do we conclude from this? Well, it's interesting. So the models have very similar behavior overall in terms of scientific prediction. The heterogeneous case, it makes sense intuitively that it has higher variance. We went to different GPUs, we went to different sites, things are just mixed up differently. Sometimes we use 2 GPUs or 4 GPUs. And so, yeah, it makes some sense that the variance was higher. What doesn't make as much sense immediately is that there seems to be some benefit. It seems to generalize a little bit better from doing this kind of variable approach. And so we're still kind of investigating exactly what those causes are, but it was surprising and very, very interesting. Second conclusion, users can leverage resources all across the country from a single OSPool access point, including NAIRR allocations using the Condor Annex. We also discovered along the way that the annex was built on some assumptions that don't quite hold up in this ecosystem, don't quite fit well in our desire to really automate things. And so work is ongoing on that front. Hopefully news very soon. And then finally, what are we doing next? So we're going to be really, really pushing on automation. One of the things we're really interested in showing is that we can do kind of a full stack training process. We can generate simulated data. We can use that simulated data to train a process. then we can fine tune that model on kind of wet lab data. And again, we're going to be working with the Tony Gitter's lab to do this on kind of single protein language models, where we were doing kind of a more generalized global model now. So we have started this work already. I wanted to include this slide because it shows, again, the power of thinking about how many epochs can I do, what can I do when I get a GPU literally anywhere. So this, again, the single protein model, it has lower memory requirements, it has lower time of training, there's less preemption risk, there's just more GPUs available to do this work. And so in the week that I've kind of been running things, I'm constantly seeing 30 to 40 GPUs going at once. We've done about 400 epochs of training already. It's not really apples to apples comparisons because it's a different model, but man, is it fun to see that line go up and to the right. And because this is the vibe coding session, I will point out that Claude happily made this visualization for me. The other thing I like to point out here, we have already run on 14 different GPU models, including some from over a decade ago, some 1080 Ti's and some P100s. So final conclusions. The first one, the name of the talk here, the path to NAIRR is open, right? So we think that the Annex and OSDF are a good way to use up allocations from a single access point. Like I said, there's gaps here. There's some rough edges, but we're working on sanding down those edges, but those edges and the integration is proven. And second, high throughput computing principles hold really, really well for machine learning. If you start thinking about how many epochs can I get done in a day, if you think about submitting locally, running globally, kind of minimizing the size of those epochs, you can really, really get a lot of throughput in some of these training processes. You always want to think about moving the work and the data to the compute, and it seems to be working really, really well. We are showing that even using heterogeneous GPUs are a valid way to do computing and training. And you should always, always have work in the queue. Marone got very grumpy with me if I did not have jobs ready to be running. Final point here, come talk to us. Whether you're kind of just getting started with machine learning workflows, or you kind of feel like you're starting to outgrow the OSPool, find me in one of the breaks, talk to the facilitation team. We'd love to get you going. Thank you.
Thanks, Ian. Good talk. Is your setup available somewhere for people to look at if they wanted to implement something similar? Or are there plans to make it available?
I have had plans, so it's fairly specific to this task at the moment. As I was writing it, I was trying to keep it general, but in the interest of time, it became more and more specific as time went. If there is interest, basically it is a sort of machine learning training DAG generation suite. And so if there is interest, I can clean it up and advertise it.
You showed graphs that showed how well the model's trained. What about any metrics on the time lag imposed by transporting the checkpoints? In other words, kind of to your point of having data ready for the next epoch to run. How was performance there?
Yeah, so I was keeping close track of sort of data transfer times as well. I was able to spot sometimes the OSDF was having issues, and I would say, oh, well, normally it's 6 minutes to move the 20 terabyte or 20 gigabytes in. Suddenly it jumped up to 2 hours, and we spotted a few sites that had gone bad over a weekend type thing. But I did not do any comparison of, does that data movement kind of cost you more than it's worth? Because, the whole idea is that more GPUs exist out in the OSPool and in NAIRR than most users have access to locally. And so, GPU availability is better than waiting 10 minutes to move data in.
All right. Thank you, Ian.